Hi, welcome to Ordinary Differential Equations. Today's topic would be numerical methods. In particular, we are going to talk about Euler method. A more advanced version of it is called the Runge-Kutta methods, especially RK4. We just mention it by name and give a location of an app that you can use to solve some equations. So what is at stake here? You remember in the last section we had a list of methods such as separation, integrating factor, exact equation, substitution, and so on. We went through some of these things. For substitution we mentioned several of them. Sorry. And then we said, well, we must be very fortunate that the equation that we are solving fall into these categories, that they are like homogeneous or Bernoulli or linear or something, that we can make a substitution and make the method work, and I get an exact solution. But that is actually a rarity. If you come across an equation, chances are we cannot solve it exactly. We have to resort to numerical approximation. So numerical approximation is a course all by itself, sometimes called numerical methods. We have something called Math 4315, which you can take and learn about how to do everything you have learned in mathematics so far, but do it approximately. So today we are going to go ahead and mention what is this numerical approximation for solving differential equations. The most basic of these is called the Euler method. So we're going to look at the Euler method in detail. And there's a long list of methods for solving numerically. We just mentioned them by names, and hopefully you take the next class and learn about them. So let's go ahead and see what we have here. So we have always a differential equation. Y prime is equal to some function of, say, x and y, or it could be t and y, or any two variables that you have here, so long as you consistently have a ratio, the derivative of your dependent variable to your independent variable. And then you have a well-formed function in terms of x and y on the right-hand side. With any of these differential equations, we have an initial condition. Initial condition means a pair of numbers, one of them representing your initial x value and the other one representing your initial y value. So this is going to be our initial condition. And then we want to solve the equation. So what is the idea? The idea is that y prime or dy dx represents a slope. So whatever you have right hand side represents slope at a given point. So if I'm in the xy coordinate coordinate plane, and I have some location x and y, at that location plugging the values of my coordinates in my right hand side is going to give me a number. What that number represents is a slope. Slope means at what rate the function is going to ascend or descend at that point. So what we are going to do in the Euler method is just take a clue from this and just travel in that direction. So this is telling us at what slope the function is going to move, and we are just going to move accordingly. Next question comes up, well, how far are we going to go in that direction? The issue is that as soon as you move, your x and y is going to change, and your slope is going to change. So imagine a boat at sea that calls to a central station, asks for the direction, and then goes in that direction. Now, every now and then the boat wants to call back and get a correction for the course they are taking. it would not be practical to call every second and redirect yourself. That would be like a GPS system that constantly says recalculating. You have to give yourself a little bit of time and move, and then do this thing in a reasonable way. To make it simple for ourselves as to how far to go before we call central in asking for new direction, we are going to have something called step size or run or h or something. So h or delta x or delta t or step size or any kind of a name of that type, it indicates to us how far to go horizontally before we recalculate our slope and perhaps make a correction and go in a certain new direction. And again, we are going to go a certain horizontal displacement h again, and after that we do our recalculation. Okay, so the idea of a step size is something to simplify our presentation here. In practice, something more sophisticated gets to be used. So these kind of problems always have an initial condition, and they have h or delta x or increment. So another word for it would be increment. Of course, it will be x increment. And that's going to be our step size. That's also given to us. The objective, so these are givens of the problem. The objective is to find the values of the function. Well, we have, of course, we are starting x0, y0 that was given to us. We are going to find out, so this is x0, y0. Then we want to go ahead and find out x1, y1. Then we're going to go find out x2, y2. So we are going to make a table, x1, y1, x2, y2, and so on. And then stop based on some criterion. Either we have to have a certain x to reach out to, or go a certain number of steps until we stop, or some stipulation like this to for us to find these numbers. So what happens after you find x2, y2, and say x3, y3, x4, y4, x5, x6, and so on? Well, you have a polygonal line which approximates the solution that is intended by this differential equation, subject to your initial condition. So initial condition is your starting point here. The whole thing depends on your step size. If you choose a step size small, typically your result is going to be much more accurate. But then, of course, you're spending that much more time to arrive at accuracy. If you make step size large, then your picture is going to be pixelated and looks jagged and so on. The idea of advanced methods is to try to squeeze as much accuracy as we can without doing too much work. And the idea of Rank-Akadam methods and the other advanced methods is to give us a smooth picture without incurring too much cost. Okay, so that's the general idea. Now, how do we actually do this thing in practice? Well, let's take a problem that is simple enough. So our presentation problem is something that we could have done by hand. We have already done it by hand. But just so that we don't get bogged down in the arithmetic of the problem, we're just going to start with something simple. Suppose I would say, the question is solve. So here's an example. Solve y prime is equal to, say, x minus y, and y of 1 is equal to 2. with a step size of h equal to say 0.1. Well, the differential equation itself, we are familiar with that. Perhaps we could use integrating factor method to solve this thing quickly. But here we want to do it numerically. What does this mean? This is the initial condition. So this is initial condition, which means what? Which means if you label your starting point x0, and x0 is this x that is given here, then y0 is 2, which is the 2 that is given here. So this means that picture we want to draw, the starting point of a picture is 1 and 2. H means in our first flight, we are going to go so that our horizontal displacement or run, another word for this thing is you run from point to another point, your run is delta x. Well, what happens? We say x0 is 1, y0 is 2. It's a good idea to give this thing a name. Well, we said this is a slope. So slope, typically you show it by the letter m, is that right? So m at the starting point will be, well, 1 minus 2, that's minus 1. So we are going at slope of minus 1. Slope minus 1 means going this way. What happens now? Well, when you go on a slope, you have either a rise or a fall. In this case, we have a fall because we are going down. That fall is sometimes shown by letter K, sometimes shown by letter delta Y. Yeah, lots of different choices. So this is the rise or the fall from that point, which is what? Which is h times delta x. This, excuse me, h times, sorry, let me make a correction. This is, of course, h times the rise. Let's repeat ourselves. Slope is the rise over run, is that right? So the rise is the step size h times the slope. So h times m. M was minus 1, h was 0.1. So when I multiply them, I get minus 0.1. So that is our k, which is the amount we rise or fall. Well, we were at 2. We fell by 0.1. So our new location is going to be, so now we say, okay, we went to the point, next point, y1. It was 2, and then fell this much, minus 0.1. So now we are at 1.9. Well, what is my x? Well, my x, that is the x of 1, is whatever I was before, plus this h that I have moved horizontally. So x is going to increment by my run. So 1 plus 1.1 is going to be 1.1. Okay, so x1 is 1.1, y1 is 1.9. So we have arrived at this point, 1.1 and 1.9. Okay, the whole thing is to repeat this thing over and over again until you are satisfied about your destination, which means what? So go ahead and calculate your slope as now the current point. So m is x minus y. X minus y is the current value of x and y. So it's 1.1 minus 1.9. Your subtract is minus 0.8. So previously my slope was -1, now my slope is -0.8, which means I'm not falling as fast as I was falling before. I'm a little bit more gentle now. Okay, now what is my rise at this situation? My rise is going to be my new slope times the h that we kept fixed in order not to make our life too complicated. So h was 0.1, the rise is -0.8, and when I multiply them I get 0.08. So now I arrived at my next point, y2. Previously it was 1.9. I fell some more. I fell by 0.08. So if it was positive, I'll add. If it is negative, I subtract. Well, if I subtract, I get 1 point, what do I get? 1.82. Well, what is my x? My x is whatever it was before plus another step size. So it's going to be 1.2. So by now my next location is 1.2 and 1.82. Okay, how many times do we do this? Typically a problem tells you how many steps to take. So you take those many steps. Or it gives you final x at which to stop. For example, perhaps if you want to stop at x equal to 2 or something. Well, if you want to stop at x equal to 2, you have to go through these steps 10 times until you get there. So the process is very simple. It's just that there are lots of arithmetic to be done. It's everything repetitive. And so you can do this thing over and over until you get to your destination. So the problems that you are going to see in this section comes into two categories. Either some formula is given to you and then you are asked to carry it out for 2 or 3 steps, in which case you just do it exactly the way we did it right now. Or if the problem asks you to do this thing, for example, for 10 steps or 100 steps or something like that, well, then you have to bring some bigger guns to do this. Either you have access to a programming language, just about any language would do, and you go write a little program. It's called a for loop or a do loop or something like that. It's something that we repeat over and over again. Or if you don't want to go after something that has too much of an overhead, I have a few things for you you can make use of. Let me open this thing. First of all, you go to your course page, and then we have Euler method software. So here's a description of the situation, description of your differential equation. Remember, you can have an x and a y or a t and a y, any kind of 2 letters would do. Here's a description of the Euler method itself. You calculate the slope, you calculate the rise, you calculate the next time, you calculate the next function value, and so on. So if you're ambitious, you either get your MATLAB or Python or Java or whatever language you have access to, and then you run it like that. However, if you want to be quick and you don't want to deal with the installation or something, you can use a variety of web apps that are available to you. So you have all sorts of these. And here is a differential equation we were just solving. So first, let me just show it like this. Let's open this thing one more time. So here is where you enter your differential equation, and then it displays it for you. So in the equation that we had x minus y. All right. And then our initial condition was 1 and 2. And then delta x is what we called h or run or step size or something, so you can control it. It's a little bit hard to exactly match it. So on the right hand side you see a table forming for you This is step 0 is where you're starting at, and then you go as far as, so well, this one goes, it looks like it goes 100 steps. That's more than enough for us. This one is geared to letters X and a Y. So it's X and a Y. You could have a T and a Y or whatever. dy dx is the slope, which we called m. Of course, you just call it dy dx here. Delta y, we called it k. That was for the rise. Of course, delta y is just as good. Well, this is step 0. That's x0, y0, m0, k0. And then you take this k, you add it to the previous one. You don't see it's minus 0.35. It gives you the next the y value. So y1 is 1.65. Delta x was 0.35 here, and then you get 1.35 and so on. The one we just did by hand, remember it was 1 and 2. Delta x was 0.1. So these are the numbers that we were just working on. And then you can go all the way to step 100. And these points are connected by a sequence of dots here. And that is if the program can solve it exactly, or solve the equation with a better method. That's how you get the red one. So the black one is the approximation, and red one is a better approximation. So you can control your problem and get your solution. So in case the problem asks you to do something for like 10 steps or 25 steps or 100 steps or something, then it is advisable to, of course, use one of these web apps. So thanks to Chip Rawlinson, who has made this thing available to us. Okay, so there are many of them. Here's another one that shows you step-by-step calculations and the numbers and everything. But that looks a little bit more crowded. If you want to check your calculations, that's the one you use. If you want to solve an equation much more accurately without going through so many steps, the method to use is so-called Runge-Kutta order 4. And here's an example of that, which has 4 rises calculated with 4 steps that we take, and we average them in a certain special way to get an accurate answer, and then you get a much better picture. So perhaps the red one here, or the orange one, is produced by RK4, and the black one is the rudimentary method, Euler method, which is the essentially the origin of all these RK methods. Okay, so that is essentially what we have to say here. Remember, what we are achieving here is a numerical or approximate solution. We don't get any formula as to what the solution look like. We just get a table of numbers. We can use this table sometimes to get an idea of how accurate it is by comparing it against a better table, or by comparing it against the exact solution, if you happen to have access to the exact solution. So in this problem, for example, x minus y, you can solve this thing by integrating factor method and compare your solution against this one. Other than that, you notice that the problem, the method is very straightforward and simple. It does not rely on any algebraic coincidence, no identities, no special functions, no fancy integration, nothing. It's very robust, and you get an answer. The problem, the con of it, is that your answer is approximate, and then you have to be careful that that approximation don't get out of hand, and though you don't produce a number that's just too far off from what's supposed to be. Well, what kind of a solution is too far off? Well, that's going to take us to the the next course, which is numerical methods. We are not going to get into that right now. That's going to be the extent of our attempt at solving problems numerically. So this is pretty much the last time we are going to have numerical solution. We are going to go back to our so-called regularly scheduled program, which is how far can we go with the calculus tools that we have based on the functions that we have learned, the exponential and sine and cosine and trig and inverse trig and logarithm and exponential. How can we combine them to make a solution? And again, we should not expect that we will be able to do that with every problem. That's unreasonable expectation. It's like we have a few keys in our pocket and expect that those keys will open every lock that we are going to see. That's of course far from the truth. But those keys help us to set up these numerical solutions and to advance us in approximate solutions. Okay, so we are going to keep this lecture short, and until next time, good luck and God bless.